Alright, so now we're going to start section 4.5, which has to do with exponential growth and decay. And so we're going to use a specific kind of function which follows the exponential growth or decay of different quantities. So first off, what is exponential growth? Well, if you see the picture over here, it shows us the graph increasing, and it increases in an exponential manner, getting larger and larger the longer we go. Exponential decay, on the other hand, is where it's decreasing, it's falling, first very rapidly, and then it kind of trails off and levels off as we go along. The function that we're going to use for exponential growth or decay is f of t equals a naught e to the kt power, or sometimes they just call it a equals a naught e raised to the kt power. So let's go through what these letters stand for. K, if it's greater than 0, is going to stand for the rate at which growth is happening in exponential growth. So basically K stands for the growth or decay rate. Because if K is less than 0, if it's a negative number, then that goes along with how fast it's decaying in the exponential decay. So that's the first thing. K is going to talk about growth or decay rate. A naught, A with a little 0 next to it, is the original amount of the quantity of the entity, whatever it may be, population or so forth, the original amount at the starting time t equal to 0. And then A is the future amount at time t. That should say time t right there. A is the amount at time t down in the future, basically. A is the future amount. Okay, at t years. So we have time t, A is the amount in the future, A naught is the starting quantity, starting amount, and K tells us how fast the exponential growth or decay will happen. Alright, now let's talk about one specific example of exponential growth or decay. It tells us that this growth model, A equals 4.3 e to the 0.01 t, this describes the New Zealand population A in millions t years after 2010. Okay, so let's think about what each of these things tell us. It gives us already the model, the function in other words, for exponential growth. The first thing to answer is, what is the New Zealand population growth rate? Well, looking up at our function, the 0.01 that's up there on the top, that's going to tell us our k value. And that's our growth rate, in other words. Our growth rate comes from the 0.01, which actually we'll say is 1%. So the growth rate is 1%. The next question is, what is the expected population in 2010? Well, 2010 is the starting year. So let me write down that right here. 2010 is the starting year. So looking at that as the starting year, we can look at our function and see that 4.3 stands for what we call A naught, which is the starting amount at the initial year. So it tells us that there should be 4.3 million starting in 2010, because that's when we start our record keeping from 2010. So that number just goes straight there inside of the function. Now, to go forward into the future, what is the expected population in 2015? So let's think about the number of years past. 2015 is 5 years after the first year that we start from, 2010. So 5 years means that time t is equal to 5. So what I'll do is I'll use this number inside the function, I'll plug it in. I'll plug it into the function a is equal to 4.3 e to the 0.1 t. So what that would do is give me 4.3 e raised to the 0.01 times 5. So this is something to calculate using the scientific or graphing calculator. If we calculate this out, we'll get approximately 4.52. So that tells us the future population, and of course it's referring to that in millions. So approximately 4.52 million. Okay, and then the last thing that it asks us is when will the population reach 5.5 million using this function. Okay, so when referring to a future amount of population, that's going to refer to the value for a. And so a, again, is our 4.3 e to the 0.01 t. So if I use 5.5 for a, it would be 5.5 equals 4.3 e to the 0.1 t. Okay, and so now in a case like this, we have to solve for t. To solve for t, we need to first move the number that's in front of e away from it. So I'm going to divide both sides by 4.3. Okay, so if I do the division here, I'm going to go ahead and divide, and I'll get 1.279. That's approximately what 5.5 divided by 4.3 is. And that's equal to e to the 0.01 t. Now since we have e to the power, I'm going to take the ln on both sides. Okay, keep in mind again that ln is log base e. So if I have log base e and e raised to the power, that's going to cancel those two things out. So what we're going to get is 0.01 t is equal to ln 1.279. And now we only need to do one more thing to solve for t. That's divide both sides by the 0.01. So t is going to be ln 1.279 divided by 0.01. So this is something we'll need to use the calculator for. If I put that in the calculator, I got out approximately 24.6. And so that refers to how many years after 2010. So 24.6 years after 2010 is when we would expect the population to get to somewhere around 5.5 million. So that would be in the year 2034, sometime in that year.